Thank you. I was very thrilled that I could sit in the audience and watch the music, because when you're on stage, you have light in your head and you can see nothing. But I know there's a lot of people in here, and I'm supposed to talk about the biodiversity crisis. It's such a negative word. What I really will talk about is life, diversity, how beautiful it is, how fantastic nature is, and the planet we live on. That's a biological planet. I'll also talk about that we should care about life. When I was a young boy, I loved to chase pigeon. I never caught one. It always flew off, but I loved it. I spent a lot of time on the patio and the terrace of my parents' hives studying ants, just observing, not playing with them, not putting magnifying glass on them, just observing them, what they did in the environment. And I had a godmother that knew my interest for nature and took me places. And she lived very close to the wildest place in Copenhagen, the zoo, and that is where she took me, and I chased pigeon. I was not so fond of the animals behind bars, but the free living spirits on earth. When I became a teenager, I started thinking about my future. And that was at the time when we started talking about that there might be life on other planets. And I decided to become a scientist to explore the unknown. When I entered university, I realized that we live on a planet that is virtually unknown. That is Earth. We don't know how many species there are on Earth. We don't know how they are distributed, at least not at that time. And we don't know what determined life on Earth. Those topics is what I will talk about in the science part of things. And those has become a definition of what I'm doing as a researcher, trying to figure out what determined diversity and distribution of life on Earth. And for that, I was lucky enough as a young student to be sent into the unknown rainforest of Ecuador with a simple task with 3 other students: go figure out what's there. It was fantastic. And we spent almost 2 years back and forth. And still today, I had the pleasure of getting a huge research grant, and I decided that I would use that grant to do what I love the most, and that is getting back in the field and back in the Andes. But life is fantastic. It occurs in all places. It occurs in the high Arctic, the high alpine zone. It occurs in lush green Denmark, which is fantastic in the spring, as we are witnessing now. Hearing the return of songbirds from Africa that is filling our sound landscape with songs. And it occurs in the deserts. It even occurs in hot springs, where water is 90 degrees, but there's life in it. And this hot spring from Yellowstone and the beautiful colors, that is made up of life. Those are bacteria that is making these colors. And if we go into where I've worked the most and where most life is, that is a humid, wet, tropical rainforest. 90% of life occur in the tropical wet forest. Most of it do not occur in the Amazon or the Congo basins, but in the mountains. What I've studied the most is mountains. These tropical rainforests that contain 90% of life on Earth has, of course, a lot of beautiful animals, and we know a lot of them. But most of them are made up of tiny insects. Actually, most of them are beetles or bugs. It's just the things that are around there. But that's most species on Earth. So, scientifically, we have described 1.7 million species. An entomologist was asked what he learned through a lifetime of work and how it related to the creation of Earth by God. And he answered that we learned that God has a tremendous fondness of beetles. If we go into the rainforest, as most places that has the largest biodiversity on Earth, it is a closed forest. It's not a savanna. It's not open canopy. It is closed. It is dense. It is difficult to work in. There is enormous amount of species. But if we describe 1.7 million, how many species are there? Well, we know that if we shake a tree in the tropics, lots of the insects that falls down will be new to science. Every year we describe new primates, new bird species. That's why we know that the 1.7 million species is not enough. There's a lot more out there. There's a lot of tree species. The Amazon is about 5 times the size of the EU. There's no path. You can move around the rivers, but Amazon is not just rivers. So how do we know how many species that are in a place like that? Well, we can do some plots. So the biodiversity in a 15-hectare plot in Burma, for example, there are 700 tree species. In all of Europe, there's 500. So just in 15 hectares in Burma, there's more species than in all of Europe. The rainforest that I used to work with in Ecuador, just 4 or 5 square kilometers, has more bird species than in all of Europe. It is tremendously diverse, but it's also a difficult place to figure out how many species are there on Earth. The trees are often 40, 50, 60 meters tall, and if you just work on the bottom, you only find a little bit of the biodiversity. We know that most of the biodiversity is up in the canopy, and that is dangerous work, and it's tedious work, and it takes a long time to just work one tree. And you might get 100 new species for science that takes about 10 years to describe. So it's an immense task to figure out how much it really is worth. So of course, as a scientist, we have tried to come up with methods that makes it easier. And one approach is to fumigate a tree. As we see here, simply put chemicals up and then have nets at the bottom. And you can see the bottom here, and you can see tiny person down there. It's a long way down. And everything that falls down at one side, you can start to count, and you could start to describe the new species. That takes a lot of time. So how do we do this for all the Amazon? How do we figure out what's there? Well, we can go in one place, like this, and just in a couple of trees, there'll be 1,200 species. There's no 1,200 species in 2 trees in Denmark. There's tremendous biodiversity, especially in the tropics. If we move not very far from here to another plot, we'll find that there is 600 new species. That's a tremendous turnover. If we move in Denmark, it basically will be the same species in the same habitat. But when we move in the tropics, we can observe that there's lots of species, and if we move not very far, there's a lot new species. There's some of the same, but lots of new species. And if we take another plot, and another plot, and another plot, we start getting information. So in each plot, we're finding out how many individuals is there of each species. And there might be 50 on one species and 30 of another species. And then there's a tail, and those are the rare ones, those that we only find one individuals of. If we do that in Denmark, there will almost be no tail. We'll have multiple examples of the same species. If we do it in the tropics, there's a long tail. But also tell us that it's very unlikely that we found everything when we're just finding one individuals. We can use information theory, actually the same mathematic methods that was used to crack the code during the Second World War is the same math that we're using, but somewhat more advanced today, to use its information of the tail to calculate how many species would be in the tree if we found everything. And when we go to another place, we can calculate what we call the turnover, how many new species are there. So now we have information on how many species will be in one area and the turnover. And from that, we can make calculations, and I'm just going to show you, one of those, and this is one of the easier calculations that we do. So it requires a lot of mathematics skills to calculate that. And when we do that, in the Amazon, when Terry Irvin, 25 years ago, started calculating how many insect species would there be in the Amazon, he came up with a staggering number of 30 million. We described 1.7, so there's a lot of difference. His calculation has been verified, tested, and we have downsized the number. So now we believe there's probably 50 million, let's just say 17 million, because then we can say we describe 10% of the world's species. So this is an example of how we're figuring out to answer a question of how many species are on Earth without finding every single one, because that would take hundreds and hundreds and hundreds of years. What I primarily have been working with is to document the diversity. This is a map of global biodiversity. We mapped every single mammal species on Earth where it occurs, every single amphibians and every single birds. And that's about 22,000 species. And when we look at this map, blue is where there's very few species. So you can see Greenland and Denmark, pretty dull species, pretty dull areas. That's why I work in the tropics. But you can also see there's an enormous amount of species in the tropics. That's the orange. But if you look at the map, there's contours, or if you know geography, you'll see the dark red where there's most species. That is in the mountain regions. So even though the mountain regions are not what is most of on Earth, they have 80 to 85% of all vertebrate species occur in mountains. Mountains are exceptionally species rich. When I started out, these maps did not exist. We did not assemble all this information. Computer made it available. And one of the first things that I did in my career was to generate these first maps of how biodiversity looks at Earth in greater details. Today, there's lots of these data, and it raises the question of where do data come from? And when I ask my students or other researchers, we're so used to that data is available that sometimes I get the answer that where do data come from? And of course, the answer is very, very obvious, the internet. That's where you get data from. But it's not like that somewhere in the internet, somewhere is generating these data. They do come from somewhere. And most of these data come from scientific collections. So for hundreds of centuries, for several centuries, we've been collecting scientific information. Darwin went out, Humboldt went out, Wallace went out, and we collected specimens ever since, and we have stored and curated them in museums. So what I did was to assemble all those information to start creating a map of life. But of course, the data do not come from museums. They come from nature. And that is why the fieldwork still today on an unknown planet like Earth is so super important. When we have data, we can start test ideas about what determines life on Earth. Let's imagine that we turn off the sun. So there's no sunlight or energy on Earth. There wouldn't be much life. If we remove all water from Earth, then there wouldn't be much life. This is why we always are looking for water on other planets, because they're important for life. So we know that energy from the sun and water is important. And we can create theories that we can test with data, and I'll show you some of these. But in terms of the biodiversity crisis, we also know that when we are altering Earth, like cutting down our forest, removing habitat for living species, so we're losing those, or when we have climate change and also changing the world, we are also losing biodiversity. But we have one big problem when we're trying to find out how much are we losing, at what rate are we losing it. And that is, we have one planet, For scientists, that is the same to have, I have a sample size of 1. And you want answers to that? We can't do that. So we have a major problem. For example, when politicians or society ask us, what will the future be when we are doing this loss of habitat or climate change? We are to extrapolate from one data point into the future. So maybe it's this, maybe it's this, or maybe here. That's a problem for us with the one Earth. If we knew how the past had looked like in greater details, we might have more data points that could tell us how this would be. This is what we call the one Earth problem. And working with this, I still really want us to find life on other planets so I have more sample sizes. Preferably with slightly different climate. The other way that this has been solved has been by doing experiments. But I think that if I and other scientists came to, global society and said, we want to do an experiment with Earth, like, for example, how about we change climate so we can see what the reaction would be? We probably would not be allowed to do that. You can't say that climate change that we have now is the experiment that could help us get some of these answers. And they have rejected a lot of our ideas as we are seeing what climate change does. This is what we call the One Earth challenge. And there are some solutions to it. We shouldn't give up because we have lots of knowledge. We know that life on Earth is basically determined by 5 processes. If we put it simple, species are born, that is speciation. Species move around in their lifetime, that is movement. They adapt to different life conditions. They interact or compete with other species or to resources. And ultimately, every species go extinct. So these are the 5 processes. We also know that these 5 processes is linked to changes in environment, for example, changes in climate. So in lack of multiple Earth and trying to get at these questions of what determines life on Earth, we can instead build virtual worlds, basically do computer simulations. So some years ago, together with paleoclimatologists, we mapped out the climate and temperature here in South America. And we heard about the ice ages, and it changes a lot. It also changed the climate in the tropics. So here is the climate temperature in South America for the last 800,000 years. And you can see that it's pulsating. There's warm period. We are in a warm period right now. Or there's in cold periods. And it impacts the process of speciation, movement, adaptations, interactions, and extinctions. So having this information and knowing what we think the process is, we can simulate Earth. And here's an example of how we do that, or the outcome of it. Here's an Andean species in South America. And if we put it in the time with the process and let it run with the changes in climate, it will spread out, it will contract. Here's a species that end up in northern Venezuela. It has changed its niche, that is, the habitat it is associated with. It's still the same species. But if it continues on, it will pulsate out, end up different places, and at one point, it will change so sufficiently that it's now another species. That is called speciation. Here the species have reached the Eastern Arc Mountains in Brazil. It came from the Andes, but it's now changed so much that it's another species. The niche has changed. Its adaptation to climate has changed. And we can run this in million years of steps. When we do that, we get a result of one example of one species. We can run this millions and millions of times, and we can see which one of these parameters, these processes that are most important. And basically what we find is that we if we look at, this idea with the energy and the water, and that determined it, we had a theory. It's called the water energy theory. We can put that and those parameters in our big simulation of Earth and says, we have an idea, and we now think that that idea is correct, and we can simulate how diversity should be on Earth. And this is basically what we find. There will be a lot of species in the Amazon, which is what we already talked about. And the nice thing with a prediction is that we can test our hypothesis by comparing it to what we observe. It's a most simple form. It's an enormous process in calculating this, but the comparison is very simple. So here's the prediction of the water energy, and here's the observed. So I talked about this tremendous biodiversity in the mountains, and our model with contemporary climate did not pick up the mountains. Basically, we failed to explain the variation of life, and we failed to explain the most species-rich places on Earth. And you don't have to do a lot of super fantastic statistics on this to see that something is wrong with the theory. And this theory and everything else that depend on contemporary climate as a primary process is not fitting what we're observing. It's still what we use to test climate change. We think it's in equilibrium with climate. I'm doing these models and forecasting the future, but we know that our basic assumption about equilibrium with contemporary climate is wrong. And when we can turn the knobs, as we say, on these simulations, we can find out which of the process are most important. And when we do that, we can also simulate something that is most closely resemble what we observe. So this is simulated, much closer to it. And we can find out two things that matter. Evolutionary process. What we see today is still a signal of things that happened millions of years ago. It is not in equilibrium with the contemporary climate. And the other thing we find is stochasticity. Just chance. Sometimes a species moves 200 kilometers. Not very likely, but sometimes it does. And maybe it lands in an area where there's suitable habitat. Very unlikely. But it could happen. That could be stochasticity. If we remove that parameters, we cannot get the end result of what we're observing. So we know movement and stochasticity, the chance, is super important. And I'll give you an example of how chance has formed life on Earth. Let's go 65 million years back to the time of the dinosaurs when they roamed the world. And I think we all heard about it. Most kids love it. It's fascinating. We probably also have observed or told our kids that dinosaurs do not exist anymore. So what happened? Well, Earth got hit by an asteroid. The Yucatan Peninsula in Mexico got hit by an asteroid. And at the same time, maybe caused by the asteroid, maybe not, but at the same time, a series of volcanoes in the oceans exploded. And it basically caused a gigantic pollution on Earth, where 75%, maybe more, of all species disappeared. It went extinct. That is a mass extinction. That is the last mass extinction we've had on Earth. It happened 65 million years ago. And we tell our kids that dinosaurs do not exist, and I'm going to tell you they do exist. They fly around. Not everything went extinct. And that time there was also some dinosaurs that kind of evolved out to what basically became the lineage of modern birds, which exploded after the erection of all big organisms on Earth. But birds are basically descendant of it. Here's another species. There was also mammals on Earth. They were small. They were mostly nocturnal. They did not rule the world. The dinosaurs did. Stephen Gould, one of the most famous paleobiologists, got asked in the 90s by CNN at the New Year party. They had a tradition that time, CNN, to ask a scientist, what is the biggest scientific realization that we've had this year? And he looked into the camera and he said, we discovered we're just lucky to be here. Mammals gave rise to humans. How would Earth have looked like if that asteroid had not hit Earth? That's a chance. That's a chance event. That's stochasticity. We have learned that many of those events really shape Earth, but it's so super difficult as a scientist to figure out what that is when it's just a chance. That was 65 million years ago that we had a mass extinction, but we also are on the doorstep of a mass extinction today. We have a biodiversity crisis, or the 6th period of mass extinction. And why do we have that? Here's again a picture of a forest. And basically what we've done, Europe should be covered in forest, Denmark should be covered in forest, most of land should be covered in forest where 90% of biodiversity is. We chopped it down. There's still a lot of forest left in the Amazon. There's not a lot of forest left in Europe. They're mostly plantations. And with the forest also disappeared, those species are in it. So up to 70% of all ecosystems in the world are destroyed or heavily disturbed by us humans. That has strengthened the living space for other organisms on Earth, and that's why they're declining. That's simple. It's not a very complex thing. And why have we done that? Well, we have agriculture. We need to feed us, and we become more and more people. We've had heavy pollution that has caused a lot of extinctions and changes in our climate, and we probably also have heard all about this, about plastic that impact all places on Earth. But ultimately, what has changed the Earth and why we have a 6th mass extinction is caused by one species, and that is us. We take up space, and we use the world resources, and we become more and more abundant. And when we calculate it, extinction is not an unnatural thing. Roughly 2 species should go extinct every year out of natural causes. It's part of evolution. But what we're seeing today is a rate of extinction that is 100 to 1,000 times higher than normal, and is predicted, if things are unchanged, to go into 10,000. That is the very definition of mass extinction. But it's not just species we're losing. We lost 25% of all individuals of butterflies. We lost 50% of all invertebrates, all the bugs that makes the world go around and actually makes the world function, or 25% of all individuals of birds. So we're also looking at a loss of individuals. And we continue this destruction of natural habitat. Some years ago, you might remember in the media that the Amazon was burning. We were very upset, and we basically told the Brazilians that they needed to get their act together. President Macron was offering 10 million euro if they could kind of, get things done right. This is a picture for one day from space of all the burning that took place. In 1 year, 5 times the size of Denmark was burned away. And this happens every year. We're not hearing it in the news anymore, but actually the rate of burning is continuing. It's very high. And we were very quick to point fingers at the Brazilian to take care of this. But we're missing a point. 60% of global biodiversity is lost due to land clearing for meat-based products. And the meat-based products is basically driven by consumers. That is me. That is you. The Western world and North America is heavy consumers of meat-based products. So it's not about pointing fingers at somebody. We're all in the same boat, and we all impact Earth by what we do and how we use resources. Let's travel 10,000 years back in time, and we have this concept of biomass. It's basically the weight or the volume of individuals. And 10,000 years ago, 99% of all biomass, all life on Earth, was made up of wild animals. And here it's put down that 1% were humans. It's probably much, much less. So how does it look today? Well, now we have 32% of all life on Earth is us, humans. And 67% is our livestock. And now for all of the rest of wild animals, there's 1%. It is dramatic change that we have done to the world. We've been through a pandemic. It's been awful. If you are a microbe, and there's millions of them that could jump from birds and mammals to humans, and they don't have strategic meetings where they decide, let's jump. But as an error trial, there's a lottery game. But the likelihood of having a jump when wild animals is just 1% of biomass and life on Earth to humans is huge. And if you land up in humans, what's not to like? There's a lot of us. We're there year after year. We're predictable. We calculated that the number of diseases that jumps to humans has went from, could potentially be pandemics, has gone from 50 years to 5 years. That's not the same that there will be a pandemic, but there's a huge increase. That's part of what we do to Earth that is resulting in that. But nature is wonderful. It's beautiful. We can decide that we like to take care of nature because it is beautiful. We like to keep it. We like to have a blue whale. That's part of the Biodiversity Convention that we should care. And we decided, all countries in the world decided, that we do not have the right to cause other species to go extinct. But we can use nature. We need to use nature. But there could also be another argument, and that is nature worth something for us? Do you like to breed? Pretty simple question. Who produces oxygen? Nature does. We haven't always had an Earth with the atmosphere that humans are adapted to. We're part of the world as it has been the last many millions with the oxygens that is produced. Nature is worth something to us. We might not go down in the supermarket and buy it, and we've had this tendency that if I can't buy it, it's not worth anything. But if you remove it, or it's not there, I think we'll realize that it's worth something. If you look at pollinations, if we take the 100 most important crops, in Denmark we only use a few, especially in tropics they use a lot, and remove the pollination, the yield would drop 40 to 90%. Remember that we're removing 25 to 50% of all the individuals that is doing these kind of things? Here's an example of coffee. I love coffee. Could I just to get an indication, how many here drinks coffee on a regular basis? Almost everyone. Imagine that that's probably also the same in many other places in the world. Coffee can be produced without pollination, but it provides a larger yields if it's pollinated. So we can put out honeybees, domestic bees, and pollinate. But what is fantastic and what this figure shows is that the more different species that pollinated, the larger yield. So if there is 4 to 6 different bees that pollinate coffee, the yield increased 10%. Imagine that the value of coffee increased 10% just by having wild bees around. So many coffee producers is now starting not to remove all of nature, but have nature associated with a coffee plantation, because it makes good sense. But a more simple thing that we can understand with nature, that is fish. A lot of economy and the development of economy comes out of our use of fish as a proteins. They are in the oceans. It's much less than it used to be. But it's not like that we're producing all the fish in a factory and then put it out in the ocean and then fish it up again. It's something nature does. It's worth tremendous. When we buy shrimps from shrimp farms, it has a value on the market. But at the same time, it also removes mangroves. It removes the fish stocks that many hundred millions people on Earth depend upon. So there is a link here. Or let's give another example. We've heard and we felt these extreme water events or weather events that is humans caused. And just last year we saw in Germany and Belgium these flooding. We saw also in Norway that houses was taken out to the sea because there was mudslides. And we're saying, oh, that's climate change. No, it's not. That's because we remove all the forest and all the vegetation that would hold back the water. So now it's coming when we have these extreme events, which is caused to come more and more frequently by climate change. But we remove nature that help us deal with it. When we're removing the mangrove, the tsunami will wipe all the way in. There's been tsunamis before, but then there was mangroves that actually stopped or lessened the effect of tsunamis. The value or the protection and insurance of these kind of things and the loss of it is tremendously high. Here's another problem that is often attributed to climate change, but it's not. The world grows 95% of its food in the top layer of soil. And we have agriculture many places. But many places, the way we do agriculture cannot sustain the use of the topsoil. We're basically using it up. We're destroying the ecosystems and the organisms that makes it work. Half of all the most productive places in the world is no longer suitable for high agriculture. So we just move on to the next place and the next place and the next place, just like we do in the Amazon, but many places in the world. But here's a problem. Earth is round, and it's not infinite. We will run out of space to move our agriculture. So we might consider another solution, that is not to destroy the ecosystem that makes these topsoil fertile. And not every country in the world can afford the solution we do in Denmark, but by doing artificial fertilizers. It's not a possibility, and we do want to feed people in the world. There's also an interaction between nature and climate. 25% of all human-caused emission comes from destruction of nature, that is, chopping down forest or removing water. We always think about that is the use of fossil energy. That's the biggest one. But nature destruction is the second one. Freshwater holds 20 to 30% of all global carbon. They only cover 5%. And what do we do and what have we done? We have tried to remove water from land because we need it for other purposes, but we caused a climate problem. I sometimes tell people that every day we should go down and kiss the ocean. If we did not have the ocean and the green organisms in it, we would have a tremendously severe climate change problem. Oceans absorb 30 to 50% of all the carbon emission we cause. Go down and kiss the ocean. We need to be thankful. It's fantastic. If we go into the sustainable target defined by the United Nations, and many of you probably know it, there's 17 of them, and we all have some that is more close to our heart than other ones. But this is the wrong way to displace the sustainability target. It ought to be displayed this way. If the biosphere and Earth do not function, we cannot solve the other problems. And the bottom of here, as Stockholm Resilience Center have defined it, is life in water, it's life in land, that is biodiversity. It is a climate and the interaction with biodiversity, and it's clean water. We really depend on clean water. Clean water is a key. When I go down in 7-Eleven and buy a bottle of water, what do I buy? I buy plastic. That is what has been produced. And then we go out in nature and take water and put on plastic. Water is crucial to our well-being on Earth. It's crucial to health. It's crucial to production. It's absolutely essential to beer production, clothes production, basically everything. But we don't manufacture clean water. We can do a little bit. So when we go on the toilet and pull out, it's dirty things. We clean it up a little bit, and next day we can do the same thing, and we just open the tap. But what happens with all the dirty water? We don't clean it up sufficiently. Nature cleans it up for us. It takes about 40 years before the same water molecule comes back to us clean, but it's been cleaned by nature. But we're destroying the ecosystem that does it. Over the last 40 years, the amount of clean water per person on Earth has dropped by 50%. There's a lot of people that is projecting that we will start having regional wars over the access to clean water. When we look at Earth and how we're using the resources on Earth, this is one way that has been portrayed, and that is that every year we're using 1.5 Earth. And of course that can't continue forever. This is why we talk about sustainable use of the resources that we have from nature. We are reaching 1 Earth on the 29th of July. That's when we use what nature produced for a year. The rest is we overusing. Denmark is reaching its part of the Earth's resources, given how many people we are, by the end of March every year. We're among the nations that has the largest footprint on Earth. This is a figure I love. And when I talked to my outreach officer and communication officer about this talk, they said, that's impossible to understand. Take it out. And they don't know that I put it back in. I think if we work a little bit together, we can understand this. It's basically talking about planetary boundaries, how much we can use of Earth. And the inner circle that is blue here, that's how much Earth provides and can sustain of pressure. And then there are different factors on it that it's using, and then it's using a symbol saying, green, it's okay, we're doing well, we can continue doing business as usual. Yellow, we should start worrying, and red, we have passed the planetary boundary of what Earth can sustain in the longer run. And if we zoom in a little bit just on biodiversity and climate change, we can see that this is the planetary boundary. And I should say that this graph and these papers are done by people working with climate change. This is the effect on climate change. So basically, we are in the yellow zone. We should worry. It's manageable. It has consequences, but we can deal with it. But for the biodiversity, there's two components here. We cross into the red. We really need to do something about this because a lot of things on Earth that sustain our well-being depends on biodiversity. The gray one is functional, that's the ecosystem service. And when they published this, they did not have sufficient data to determine it. It's coming out, and part of this research is done by people in my center, including and foremost Catherine Richardson. And I've heard that they will come out and say they have data to declare this red. I gave you a lot of figures, but we can also just sum it up as Ursula von der Leyen, the president of the EU Commission. And she's basically on all these economic values, she's basically saying, based on science, that nature provides to humans being 50% of the gross national product we're using every year, but we don't put a value on it. 50%. And we have a new biodiversity strategy. And this is her very words when she presented. It wasn't the commissioner for environment that presented this. It was the president of the commission. And tells us something about how important the view is. It is time to fix our broken relationship with nature. Climate change, loss of biodiversity, and the spread of devastating pandemics demands it. And EU have put forward Green Deal and a heavy biodiversity strategy, which we will start discussing in Denmark, because I think we're in for a shock. But EU is really pushing on this. And they stand on scientific reasons. And the good thing for this, of what we can do, is that we know a lot. The scientific foundation is really good. There's scientific consensus, and just like there is a climate panel, there's also a biodiversity panel. And they have made these reports saying, this is the problem, these are the consequences, and when we know the problems, we also know how to deal with them. It might not be easy, but we know how to deal with them. And the 137 countries in the world that's part of this panel, IPBES, has agreed that we acknowledge what science are telling us. So we no longer discuss the scientific background. We discuss how to solve the problems. So that's pretty fantastic, and it's part of the reason for why I'm actually super optimistic about solving this. And it stands on science. This is E.O. Wilson. He is the father of biodiversity. Biodiversity is a term established in 1986 by E.O. Wilson. He was one of the most influential scientists of his time. Many people say that he's a modern version of Darwin. That's how influential he's been on our thinking. When he was 86, he died last December. When he was 86, he summed up everything that he worked with and called it the half-Earth theory. Basically saying that if we are to maintain biodiversity and all the things it gives us in a healthy, manageable manner, half of Earth should be nature and half of it should be for humans. What EU has decided on, based on all this, is 30%. EU has decided that 30% of all land and 30% of all water, ocean, should be set aside for nature because of all of this. And it's also debated in United Nations. And one of the solutions is that world leaders need to agree on these. And that's not easy. But there is a COP agreement, this global agreement, on its way for biodiversity. And it also has the target of 30% preserved for nature on land and on water. So one of the solutions is to world leaders to agree. And if you ask, what can I do? Well, they are our leaders. And at least in democratic countries, we elect them. But we can also do other things. We are consumers. When you go down in the supermarket or when you buy clothes, you make decisions every time of how to use Earth. I told you that 60% of all destruction of forest, tropical forest, comes out of our consumption of meats. If we reduce the meat down to a normal standard in the Western world, they're basically just following sound health-wise about what you should eat. So it's not about becoming vegan or vegetarian. It's about reducing down to a level that out from a health perspective is healthy for us. If we reduce it by 50%, there's a new study out in a journal yesterday. Basically, if we reduce by 50% in the Western world, we can save 80% of forest. You can do a lot. I can do a lot. I love meat. I'm challenged. Here's another thing. 40 years ago, Southeast Asia was burning. We all forgot that today. But that was basically clearing out forest so we can make palm oil plantations. And it's so cheap because nature didn't cost anything. That was where all biodiversity is. This is inside. There's nothing biodiversity left. But it's so cheap that it's in so many projects that I will say it's probably between 25% and 50% of all the products we buy in the supermarket. It's one of the reasons why it's so cheap, because we haven't paid for the destruction and all the services. And if you go in the supermarket, try to figure out what you're buying. It's in toothpaste, it's in perfume, deodorant, sodas, all kinds of butter, all kinds of oil, all kinds of bread, all kinds of candy. It's in everything. And if you can't see it on the label, that's because it's been converted into something else, so there's other names for it. And the same thing with our consumption of beef. This is Brazilian rainforest. Well, it's been chopped down because we turn it into soy rows, and this is what we import in Denmark when we're complaining about the Brazilian not taking care of nature, because we are using it to produce meat. Our behavior as consumers does matter. It is being listened to. Big companies is now starting to listen to this, and they have a sustainability strategy, they have a climate strategy, but many of the biggest companies in the world are starting to have a biodiversity strategy. And that comes out of that they're foreseeing a future where we consumers are putting it on the agenda. There was a recent survey in the World Economic Forum, and they asked, what are the top 10 problems that you as a CEO for a big company have to deal with? And the top 3 was climate, extreme weather event, and biodiversity loss. It is really on the agenda. But it matters what we do. And I will conclude with a last slide. And I love this slide. And I know that it's not really in focus. I love this kid. Who is to tell him that he cannot do this? He's ambitious, but he wants to do it. I share this vision with this kid. I actually think it's doable to deal with this issue without losing prosperity and feeding the world. It is doable. We know how to do it. We know what the problems is. We just need to agree upon doing the right thing. Thank you.